63 light years from where you are lying right now, there is a planet that is blue. Not the soft blue of an ocean seen from orbit. Not the pale, washed blue of a winter sky just before dawn. A deep, electric, almost unreal blue, the colour of a sapphire held up against a candle flame. If you could somehow stand on the deck of a ship and watch it from a safe distance, you would see a world that looks, for one single deceptive moment, like a place you might know. A blue marble hanging quietly in the dark. And for that one moment you might feel something close to comfort. And then you would drift a little closer, and the comfort would come apart in your hands, because that blue does not come from water. There are no oceans on this world, there is no shoreline, no surface to stand on, nothing solid to set your feet against. The blue comes from glass, from countless tiny grains of silicate, the same family of minerals that make up beach sand and window panes and the glass on the screen you may have been holding only a few minutes ago, suspended impossibly high in an atmosphere hot enough to melt them where they hang. And those grains do not fall the way rain falls here. They do not drift down softly and gather into puddles. They are seized by winds moving faster than any storm this planet has ever known, winds that scream it around the world at thousands of miles an hour, and they are driven sideways. On this world it rains glass. The glass flies sideways, and it has been doing so without pause, without mercy, without a single quiet night, for longer than there have been eyes to witness it. I want you to let your eyes close now if they are not already closing. You do not have to hold all of this in your mind at once. We have time. We have hours ahead of us, and there is no hurry in any of it. We are going to travel out there slowly, the way light itself travels, patient and unstoppable, and we are going to take this strange and violent world apart one layer at a time, until you understand it the way the people who found it came to understand it. Where it is, what it is made of, why it glows that impossible blue, why the wind never stops, and why, when you learn what is really happening in its upper air, the word terrifying stops feeling like an exaggeration and starts to feel like the only honest word left. This world has a name, though it is not the kind of name that rolls easily off the tongue. It is called HD 189733b, a string of numbers and a single lowercase letter. There is no poetry in it, no mythology, no ancient god it was named after. It is a catalogue entry, a line in a ledger. And yet behind that cold and clinical label is one of the most extreme places human beings have ever discovered, a planet so hostile that it makes the worst weather on Earth look like a gentle afternoon. A planet that has quietly become one of the most studied objects in the entire night sky, and a planet that almost nobody outside of astronomy has ever heard of. So stay with me as your breathing slows and the room goes soft around you. There is nothing you need to do tonight except listen and drift, and let me carry you out across 63 light years of empty space to a blue point of light that has been screaming into the dark since long before your grandparents were born. Let me show you the planet where it rains glass sideways, and let me show you slowly how a handful of people on a small wet world managed to learn its secrets without ever leaving home. Part 1. Something passed in front of a star. To understand how strange this discovery was, you have to understand what astronomers were actually looking at on the night it happened. They were not looking at a planet, they could not see a planet. Even now, with the most powerful telescopes humanity has ever built, HD 189733b has never been photographed as a world. It is too small, too dim, and far too close to the blazing star it orbits. Against that glare, it is a candle held next to a lighthouse. So when I tell you that on the 5th of October in the year 2005, a team of astronomers in France discovered this planet, I do not mean that they saw it. I mean that they saw something far more subtle. They saw a star flicker. The star is the thing you can actually find in the sky. It is called HD 189733, and it sits in a small and unremarkable constellation called Vulpecula, the little fox, a faint scattering of stars tucked between the bright shapes of Cygnus the Swan and the Arrow of Sagitta. If you knew exactly where to look, and you had a clear dark night and a decent pair of binoculars, you could find that star yourself. It glows near a soft smudge of light called the Dumbbell Nebula, a dying star's exhaled shell of gas that amateur astronomers love to hunt for. The host star is bright enough, close enough, ordinary enough that for most of human history it was just one more point of light in a crowded patch of sky. Nobody had any reason to give it a second thought. But a team of French astronomers, led by a researcher named François Bouchy, was watching that particular star very carefully. And what they were watching for was a dip A tiny, regular, almost imperceptible dimming. Because here is the thing they understood, the simple and powerful idea that makes everything else possible. If a planet orbits a star and if the angle is just right so that the planet passes directly between that star and the Earth, then every time the planet crosses the face of its star, it blocks a sliver of the star's light. The star gets very slightly fainter, and then the planet moves on and the light returns. A flicker, a shadow crossing a lamp, a dip in a graph that, if you did not know what you were looking at, you might dismiss as noise. They did not dismiss it. The dip they found was deep, deeper than most. This planet blocks roughly 3% of its star's light every time it passes by, one of the largest such shadows ever measured at the time, which told them immediately that whatever was crossing in front of that star was big, Jupiter-sized, a giant, and it was orbiting fast, completing a full circuit of its star not in years, not in months, but in just 2.2 days. Let that number settle for a moment, because it is the first clue to everything strange about this place. A year on this world, one complete trip around its sun, lasts barely longer than a long weekend. Think about what that means. Earth takes 365 days to circle the sun, and we sit at a comfortable distance of 93 million miles, far enough that the sunlight reaching us has cooled into something gentle and survivable. This planet circles its star in 2 days. To do that, to move that fast and not go flying off into space, it has to be locked in close, terribly close, far closer than any planet in our own solar system rides to our sun. It orbits at roughly 1/30th of the distance between the Earth and the sun. Mercury, the scorched innermost world of our own system, the one so close to the sun that its daytime surface could melt lead, is more than 3 times farther from our star than this planet is from its own. This world is not warmed by its star. It is held against its star like a hand held over a fire that never goes out. And so already, on that October night in 2005, before anyone knew anything about glass or blue light or sideways wind, the astronomers in France knew this much. They had found something enormous, orbiting something bright, impossibly close and impossibly fast. They had found a giant pressed against a furnace. Everything else, every terrible and beautiful detail we are going to uncover tonight, flows from that single fact. Stay with me and let it pull you forward into the dark, because the next thing they learned was what kind of monster lives that close to a star, and the answer has a name, and the name is Hot Jupiter. Part 2. The Star That Holds It. Before we go any deeper into the planet, I want to spend a little time on the star, because you cannot understand this world without understanding the fire it orbits. We tend to think of stars as distant and unchanging, fixed points that have always been there and always will be. But a star is a thing that lives, it burns, it flares, it breathes out radiation in waves. And the particular star that holds HD 189733b is not a calm one. It is what astronomers call a K-type star, a kind of orange dwarf, slightly smaller and slightly cooler than our own sun, with a more muted, more amber light. If you could stand at a safe distance and look at it, it would glow a warm orange rather than the white gold of our daytime sky. In the great catalogue of stars, this is a fairly common kind. They are smaller than the sun, they burn more slowly, and they tend to live far longer, which has made them favourites among scientists who wonder where life might one day be found. A calm orange dwarf with a planet in the right place could, in principle, be a cradle. This star is not that. This star has a planet pressed up against its skin, and it treats that planet accordingly. Here is something that should sit with you. This star is bright enough and close enough to us that you do not need a great observatory to find it. On a clear night with binoculars, near that little smudge of the Dumbbell Nebula, you could locate the exact point of light that this entire story orbits. The photons hitting the lens of your binoculars would have left that star 63 years ago. They would have crossed 63 years of empty space untouched, unbothered, to end their journey in your eye on a quiet night while you stood in your yard. And somewhere in that light, woven invisibly through it, would be the faint fingerprint of the planet that crosses its face every 2 days. You would not see the planet, but it would be there, in the light, the way a voice is in a recording even when the room is silent. Now here is where the star turns from a pleasant orange point into something more menacing. Because this star is active, it is restless. It produces powerful eruptions, flares of radiation, and it bathes its close-in planet in a torrent of high-energy light that would be lethal to anything we would recognize as alive. Scientists have measured it. The planet, sitting where it sits, is hit by extreme ultraviolet and X-ray radiation at a rate that is staggering to imagine. When you account for how close the planet is and how large it is, astronomers calculated that it receives an X-ray dose around 3 million times greater than the dose the Earth gets from our own Sun during a flare at the edge of its strongest class. 3 million times. Read against that number, our planet's relationship with the Sun starts to look like a tender and careful thing, a fire kept at a respectful distance by 93 million miles of darkness. The star is also old enough and stable enough to have held this planet in its grip for a very long time, billions of years, long enough that everything we are going to describe, the heat, the wind, the glass, has had eons to become the steady, brutal, unchanging condition of that world. This is not a passing storm. This is not weather in the way we mean weather, something that comes and goes, something you wait out. This is the climate of the place, it is what the planet is. And it has been that way since before the first single-celled life stirred in the oceans of the world you are lying on right now. I find something almost unbearably moving in that, and I want you to feel it too as you drift, while the very first living things on Earth were just beginning, blind and soft and small in the warm shallows of a young ocean. That planet 63 light-years away was already there, already blue, already burning, already raining glass into a wind that screamed and had no one to scream for. It did not wait for us. It did not need us. It simply was and is and will be indifferent and incomplete, a fact about the universe that happened to be true whether or not anyone ever looked up and found it. But someone did look up. Someone did find it. And once they had found that telltale flicker, that 3% shadow crossing an orange star every 2 days, the real work began. Because finding a planet is only the beginning. The harder question, the question that would take the better part of 2 decades and some of the finest instruments ever made to answer, was simpler and stranger than anyone expected. What is it actually like out there? What would it feel like to fall toward that blue point of light? Stay with me, we are going to find out. And the answer begins with understanding exactly what kind of beast a hot Jupiter truly is. Part 3, the monster called a hot Jupiter. There is a word astronomers use for planets like this one, and the word is almost gentle. They call it a hot Jupiter. It sounds harmless, almost cozy, the way you might describe a summer afternoon, but there is nothing cozy about it. A hot Jupiter is one of the strangest categories of world in the entire catalogue of planets we have found, and when the first one was discovered it broke nearly everything astronomers thought they understood about how solar systems are supposed to work. Here is why. In our own solar system, the arrangement makes a kind of intuitive sense. Close to the Sun, where it is hot, you find the small rocky worlds, Mercury, Venus, Earth, Mars, compact, dense, made of stone and metal because the fierce heat near a young star tends to boil away the lighter gases and leave only the heavy stuff behind. Then far out where it is cold you find the giants, Jupiter, Saturn, Uranus, Neptune, vast balls of gas and ice, swollen and slow, taking years and decades to crawl around the Sun. Big planets live in the cold far reaches. Small planets live near the fire. That was the rule. That was how it was supposed to go. And then, beginning in the mid-1990s, astronomers started finding giant planets, Jupiter-sized monsters, parked right up against their stars, closer to their suns than Mercury is to ours, whipping around in days instead of decades. It was as if you'd walked into someone's home expecting to find a goldfish in a bowl, and instead found a whale crammed into the kitchen sink. It should not have been possible. A gas giant should not be able to form that close to a star, where the heat would tear apart the gas before it could ever gather. So how did they get there? The leading idea is that these giants form far out in the cold the way they do here, and then over millions of years they spiral inward, migrating slowly toward their star until they settle into a tight and final orbit. A long fall that ends with the planet baking against the very fire that should have prevented its existence. HED 189733b is one of these wanderers. It was not born where we find it. It journeyed there. It fell. And once a giant has fallen that close, something happens to it that I want you to really sit with, because it shapes everything about the world we are describing. The planet becomes tidally locked. The same gravitational forces that keep our own moon, showing only one face to the Earth, forever. The near side we know and the far side we never see grip this planet far more fiercely. One side of HD 189733b faces its star always. The other side faces the dark always. There is no sunrise there. There is no sunset. There is no rotation of day into night the way your body has known its whole life, the slow turning that tells you when to sleep and when to wake. On one half of that world it is eternal blazing noon, and on the other half it is an eternal starless midnight, and the line between them, the thin ribbon, where the two halves meet, is the only place that is neither one nor the other. Now hold those two facts together. A giant ball of gas, the size of Jupiter or a little larger, pressed close against an active orange star, with one face cooking forever and the other face frozen in shadow forever. What do you think happens to the air between them? What happens when one side of an atmosphere is enormously hotter than the other, with no rotation to even it out, no night to let the hot side cool? The answer is that the heat does not stay put. Heat never stays put. It moves. It rushes from where there is too much of it toward where there is less. And on this world that rush is not a breeze. It is not a gust. It is a permanent planet-spanning torrent of moving air that we will come to in time, the engine that drives the glass. But first, understand the temperatures we are dealing with, because they are difficult to hold in the mind. On the day side, the side that faces the star and never looks away, the atmosphere reaches temperatures of over 1,000 degrees Celsius. Some measurements push it higher still, towards 1,700 degrees Fahrenheit and beyond, hot enough to melt copper, hot enough to soften iron, hot enough that the very minerals we think of as the most solid and permanent things on Earth, the rock and the sand, would run like water. This is not a place where it is merely very warm. This is a place where the concept of solid ground has no meaning, where stone itself becomes vapor, where the idea of standing somewhere collapses entirely, because there is nowhere that is not either burning gas, or frozen gas, or screaming wind, and there is no surface. I want to make sure that lands, because it is so unlike anything in your experience. When you imagine a planet, you imagine standing on it. You imagine ground beneath your feet, a horizon, a place to be. HD 189733b offers none of that. It is a gas giant, which means that if you fell toward it, you would never land. You would simply sink. The atmosphere would grow thicker and thicker around you, hotter and hotter, denser and denser, the pressure building like the weight of an ocean, and they're far beyond the weight of any ocean, until you were crushed and cooked and dissolved long before you reached anything you could call a bottom. There is no bottom in the way you mean it. There is only deeper and hotter and worse. The blue you would have seen from far away is not a surface at all. It is the top of an atmosphere, a layer of haze and cloud and flying glass. And below it there is nothing but more of the same, going down and down into a darkness no light and no creature and no machine could ever survive. So that is the monster. A fallen giant, locked in place, half of it on fire and half of it in shadow, with no ground and no night and no mercy, holding 1,000-degree atmosphere against the side of a star that pours 3 million times the radiation onto it that the Earth has ever felt. That is the kind of world we are talking about. And the astonishing thing, the thing I keep coming back to, is that we know all of this. We know it in detail. We have measured the temperature of a planet 63 light-years away that no telescope has ever truly seen. Stay with me, because the question of how we know is, in some ways, an even stranger and more beautiful story than the planet itself. Part 4. Reading a world we cannot see. I keep saying that no one has ever truly seen this planet, and I want to make sure you understand that I mean it literally. There is no photograph of HD 189733b as a globe. There is no image of its clouds, no portrait of its blue face, no picture you could point to and say, there, that is the world. Every illustration you may have come across. Every gorgeous painting of a deep blue sphere wrapped in cloud is exactly that, a painting. An artist's careful imagining, built on what the measurements imply. The planet itself in every real telescope is invisible. It is lost entirely in the overwhelming brightness of the star it hugs. Trying to photograph it would be like trying to photograph a moth flying in front of a stadium floodlight from miles away. The light of the star drowns it completely. And yet we know its temperature. We know the colour of its sky. We know what its atmosphere is made of, what chemicals float in its air, how fast its winds blow and in which direction, and even that it is slowly bleeding away into space. How? How is any of that possible for an object we cannot photograph? The answer is one of the quiet triumphs of human cleverness, and it begins with that same simple trick that found the planet in the first place. The transit, the shadow, the dip in the light. Here is the idea, and it is so elegant that I think it is worth slowing down for. When the planet passes in front of its star, most of the star's light comes straight to us, untouched. But a thin sliver of that light, the light that grazes the very edge of the planet, does not come straight to us. It passes through the planet's atmosphere first. It travels through that ring of air around the planet's edge before continuing on across 63 light years to our telescopes. And as it passes through that air, something happens to it. The gases in the atmosphere absorb certain specific colours of light. Not all colours, particular ones. Each kind of gas, each chemical, has its own signature, its own set of colours it drinks in and its own set it lets pass. Sodium drinks one set, water vapour another, each one leaves a fingerprint. So astronomers do something patient and ingenious. They measure the star's light very precisely when the planet is not in front of it, getting a clean baseline, the full unfiltered spectrum of colours. Then they measure it again, with exquisite care, while the planet is crossing, when that thin sliver of starlight has just passed through the planet's air. And they compare. The tiny differences between the two, the specific colours that go missing during the transit, are the fingerprints of whatever gases that starlight passed through on its way out of the planet's atmosphere. By reading which colours disappeared, they can read the chemistry of an atmosphere they will never visit and never see 63 light years away from a few dips in a graph. They call this transmission spectroscopy. And it is, when you really think about it, a kind of magic that happens to be true. Starlight goes on a journey through an alien sky, and it carries the secrets of that sky home to us, written invisibly in the colours it lost along the way. There is a second trick too, just as clever. As the planet circles its star, sometimes the planet itself slips behind the star, vanishing for a moment from our line of sight. Just before it disappears, we are receiving light from the star plus a tiny bit of light and heat coming from the planet itself, from its glowing hot day side. Then the planet goes behind the star, and for a while we get only the star's light alone. By subtracting one measurement from the other, by taking away the star alone from the star plus planet, what remains is the planet by itself, its faint heat, its own glow. From that, astronomers can take the temperature of a world they cannot see, measure how the heat is spread across its face, even watch how that heat shifts as the planet turns its hot day side toward us and then away. This is how they built the first ever map of temperature across the face of a planet beyond our solar system, and the planet they built it for was this one. We will come back to that map, because what it revealed about the wind is its own quiet horror. Sit for a moment with what all of this requires. To measure these things, you are not looking for a big obvious signal. You are looking for changes of a few parts in 10,000, a whisper of a difference in the brightness of a star, teased out of instruments cooled to almost absolute zero, corrected for every flicker of our own restless atmosphere, stacked and averaged across many transits to pull the truth up out of the noise. People spent careers on this. People built telescopes the size of buildings and launched others into orbit above the blur of our air, all to read the faint handwriting of starlight that had brushed against an alien sky. And it worked. Slowly, transit by transit, year by year, the blue planet gave up its secrets. The first one, the one that made headlines around the world, the one that gave this planet its strange and beautiful reputation, was the secret of its colour. Stay with me, and let me tell you how a handful of scientists discovered, from a dip in a graph, that there is a world out there the colour of a deep blue jewel. Part 5, The True Blue Planet. It was the summer of 2013 when the news went out, and it travelled fast because it was the kind of fact that lodges in the imagination and refuses to leave. Astronomers using the Hubble Space Telescope had, for the first time ever, measured the actual visible colour of a planet beyond our solar system. Not inferred it, not guessed at it, measured it, the way you might measure the colour of a wall. And the answer came back deep and rich and unmistakable. The planet was blue, a cobalt blue, an azure blue, the kind of blue you find in a sapphire or in the deepest part of a clear ocean. A team led by an astronomer named Frédéric Pont had pulled this colour out of the dark, and they published it in a scientific journal in the first days of August that year, and suddenly this catalogue entry, this string of numbers, had a face. It was the blue planet. I want you to understand how hard this was because it makes the results so much more beautiful. Remember, you cannot photograph this planet. You cannot point a camera at it and read off its colour the way you would with a flower or a stone. The astronomers had to do something far more delicate. They watched the planet as it passed behind its star, that second trick we talked about, the one where you subtract the star alone from the star plus planet. They measured how much light the planet reflected at different colours just before it slipped behind the star and vanished. And what they found was that the planet reflected blue light far more strongly than it reflected red or green light. When light fell on this world and bounced back toward us, the blue came back bright and the rest came back dim. A world that bathed in its orange star's light throws back a deep and glowing blue. Now here is the part that turns the beauty into something colder. On Earth, our world looks blue from space for two reasons, both of them gentle. Part of it is the ocean, the vast mirror of water reflecting the sky, and part of it is the air itself, the way our atmosphere scatters blue light from the sun in all directions, the same reason the daytime sky over your head is blue and not black. Both of those are soft, familiar, life-giving things. Water and air, the cradle of everything you have ever known. You might be forgiven, looking at that distant blue point, for hoping even for a heartbeat that the same gentle causes were at work out there. That somewhere in that blue there might be water, or a sky like ours, or some faint echo of home. There is not. The blue of HD 189733b does not come from water, because there is no liquid water there, and could never be at those temperatures. It does not come from a gentle sky scattering its starlight. The blue comes, the astronomers concluded, from clouds. But not clouds of vapour or ice the way ours are made. Clouds laced with silicate particles, tiny grains of mineral suspended in an atmosphere so hot that those grains form by condensing directly out of vapour, the way water droplets condense out of humid air, except that what is condensing here is the stuff of glass. High in that blowtorched atmosphere, in a haze of these mineral grains, blue light scatters more strongly than red, just enough, just so, to make the whole world glow that deep electric blue. The colour you would have found so comforting from a distance is the signature of the very thing that would kill you. The blue is the glass. Read that again as you drift, slowly, the way it deserves. The thing that makes the planet beautiful is the thing that makes it lethal. The serene cobalt glow, the jewel hanging in the dark, the colour that for one moment looked like home, is the light scattering off a sky full of molten mineral grains, grains that are forming and falling and being flung sideways in a wind we have not even properly described yet. There is a lesson hidden in that somewhere, about how the universe wears its dangers, how the most hostile places can dress themselves in the gentlest colours, how a thing could be lovely and deadly at the very same instant and in the very same way. But I will leave that lesson to settle into you on its own. We have a planet to keep exploring, and the next question is the obvious one. What exactly is this glass? Where does it come from? And why does it rain? Part 6. What the glass actually is. When you hear that it rains glass, your mind probably reaches for the most familiar image. A pane of window glass, a drinking vessel, something clear and hard and sharp shattering. That image is close enough to be useful, but the truth is both strange and, in a way, more elegant. So let me take a moment to tell you what the glass on this world really is, because understanding it is the key to understanding the rain. Glass, here on Earth, is mostly made from sand, and sand is mostly made from a mineral called silica, which is silicon and oxygen bound together, the same elements that make up a huge fraction of the rocky crust beneath your feet. When we make glass in a furnace, we heat sand until it melts, until those rigid mineral structures soften and flow, and then we shape it and let it cool. The whole trick of glass is heat. Heat turns the solid mineral into something molten and workable. Take away the heat and it sets again, hard and smooth and clear. Now carry that idea out to HD 189733b. The atmosphere of that planet is rich in these same kinds of materials. Silicates, the mineral building blocks of rock and sand, present not as solid stone but as vapour, because the temperatures are so extreme that minerals which would be hard rock on Earth exist there as gas. Imagine that, an atmosphere where the air itself carries vaporized rock the way our air carries water. And just as our air, when it cools, lets its water vapour condense into droplets and clouds and rain, this alien air, in its slightly cooler regions, lets its mineral vapour condense. The silicate vapour cools just enough to gather into tiny droplets and grains. Droplets of molten mineral, grains of forming glass. They are not the cold clear glass of a window. They are searing hot, glowing, half-melted beads of silicate, condensing out of a sky of vaporized stone. And those grains are small. We are not talking about hailstones or sheets of window pane crashing down. We are talking about particles so fine they are more like a glittering mist, a haze, each grain microscopic, suspended high in the atmosphere where it scatters that blue light we just talked about. This is what makes the clouds. This is what makes the colour. A high haze of countless tiny molten glass beads, each one a fleck of rock that has been heated to vapour and then cooled just enough to gather into a droplet, floating in an air that would incinerate anything we know. So when we say it rains glass, here is the picture to hold. In the cooler layers of that atmosphere, perhaps on the night side where the eternal shadow lets the temperature fall a little, silicate vapour condenses into these tiny molten grains, the way water condenses into droplets in a cloud. And those grains, being heavier than the gas around them, want to fall. On a calm world they would drift gently downward, a slow soft fall of glittering glass, a strange and almost gentle snow of mineral. That alone would be one of the most beautiful and alien sights in the cosmos, a quiet fall of glowing glass beads through a deep blue sky. But this world is not calm. This world has the wind, and the wind is what takes that gentle fall of glass and turns it into something out of a nightmare. Because the wind on HD1 89733b does not allow anything to fall straight down. The wind is so violent, so relentless, so much more powerful than the planet's pull, that the falling glass never gets to fall. It is caught mid-descent and hurled. It does not rain down, it rains across. It flies sideways, parallel to the planet, driven horizontally by a current of air moving at speeds that on Earth would be physically impossible. A wind that would be the loudest and most destructive force any of us could imagine, screaming around an entire world without ever once stopping to rest. So before we describe that wind, sit for just a moment longer with the glass itself. A sky full of tiny molten beads of vaporized rock, glowing faintly, scattering blue light, trying to fall, never allowed to. That is the rain. It is not water. It was never going to be water. It is the planet's own substance, its rock and its minerals, lifted into vapour by impossible heat and condensed into glass and then flung across the sky forever. Stay with me and let me finally show you the wind, the engine that drives all of it. Because we did not just guess at that wind, we measured it. We made a map of the weather on a planet 63 light years away, and the number that came back is one of the most astonishing in all of astronomy. Part 7. The first weather report from another world. In the year 2015, a small team of astronomers at the University of Warwick in England did something that had never been done before in the history of our species. They measured the weather on a planet outside our solar system. Not the average temperature, not a single number for the whole globe, the actual movement of the air, the wind. They tracked how fast it was blowing and in which direction, and they assembled it into something we can fairly call the first weather map of an alien world. And the planet they did it for was this one, the blue planet, HD 189733b. The way they did it relies on a piece of physics you have already experienced without thinking about it, even if you have never put a name to it. You know how the sound of an ambulance changes as it races past you. As it comes toward you, the siren sounds higher in pitch. As it moves away, the pitch drops. The sound has not changed at all from the ambulance's point of view. What has changed is the motion between you and the source. When something that is making waves moves toward you, the waves get squeezed together and arrive more quickly, raising the pitch. When it moves away, the waves stretch out and the pitch falls. This is called the Doppler effect, and it does not only happen with sound, it happens as with light. Light from something moving toward you gets shifted very slightly toward the blue end of the spectrum, its waves squeezed. Light from something moving away gets shifted very slightly toward the red, its waves stretched. The shifts are tiny, far too small to see with your eyes, but instruments can measure them with breathtaking precision. And here is the brilliant thing the Warwick team realised. If you watch the planet's atmosphere as it transits, and you look at the fingerprint of a particular gas, in this case sodium, you can measure the Doppler shift of that fingerprint. You can see whether the air on one side of the planet is moving toward you, and the air on the other side is moving away. And from that, from the tiny colour shifts in the absorption of sodium in an alien sky, you can read the wind. What they found was almost beyond belief. The winds on HD 189733b they measured blow at speeds of up to around 5,400 miles per hour. Let me say that again slowly, because the number is so large that it tends to slide right off the mind without registering. 5,400 miles per hour, roughly 2 kilometers every single second. That is around 7 times the speed of sound. 7 times. The fastest fighter jets humanity has ever built strain and burn enormous amounts of fuel to break the sound barrier even once. The wind on this planet exceeds it by a factor of 7 everywhere, constantly, as the ordinary background condition of the place. Bring that home to Earth for a moment so you can feel the scale of it. The most violent hurricanes our planet has ever produced, the great storms that flatten coastlines and that we name and fear and remember for generations, top out somewhere around 200 miles per hour at their most ferocious. 200. That is the worst our world can do, the absolute ceiling of terrestrial wind. The kind of gust that tears roofs from houses and uproots ancient trees and rewrites coastlines in an afternoon. The wind on HD 189733b is more than 25 times faster than that. If you could somehow take the most destructive hurricane in recorded history and multiply its fury by 25 and then make it permanent, make it cover an entire planet, make it never weaken and never pass and never let up for a single second across billions of years, you would have something approaching the ordinary weather on the blue planet. And it blows in a particular direction, which is the final piece of the engine. Remember the tidal lock, one side always facing the star, blazing hot, one side always in shadow, merely terribly hot. The heat builds on the day side with nowhere to go, and it tears around the planet from the hot side to the cooler side, racing along the equator in a band that wraps the whole world. The Warwick measurements showed exactly this kind of pattern. Air rushing from the searing day side toward the night side. Oh, an enormous river of atmosphere flowing around the planet, carrying its heat and carrying locked up inside it the glass. This is the wind that catches the falling silicate grains and refuses to let them fall. This is the current that turns a gentle snow of glass into a sideways scream. The weather report from 63 light years away comes back as a single brutal sentence. The wind never stops, it moves at 7 times the speed of sound, and it carries glass, day with me, because now we can finally stand inside it, and imagine what it would actually be like to be there. Part 8. Standing in the storm that has no end. Let us do something impossible together. Let us pretend, just for a little while, that you could be there, that you had a body that could not be harmed, that could not be burned or crushed or torn, and that you could descend into the atmosphere of HD 189733b and simply observe, the way a ghost might observe, untouched by everything around you. I want to take you down into it, slowly, layer by layer, so that you can feel the place, rather than only know its numbers. Settle in. There is no danger here in your bed, under your blankets. The danger is 63 light years away. We are only going to look. You begin high above the planet, in the dark, with the orange star burning steady and unblinking off to one side. Below you spreads the blue. From here it is still beautiful, still that deep electric cobalt, soft and glowing, the whole curved face of a world the size of Jupiter laid out beneath you. There is no green, there is no white swirl of familiar cloud, there is no brown of continents or the wrinkle of mountain ranges. There is only that endless, uniform luminous blue, vast beyond comprehension, the largest single thing you have ever seen, glowing faintly from within as the starlight scatters through its haze of glass. You begin to fall toward it, and the first thing you notice is that the blue is not still. It is moving. The whole surface of the atmosphere is flowing, streaming, racing in one direction in great smooth currents, faster than your eye wants to accept. It is like watching a river that fills the entire sky, and as you sink lower into the haze itself, the gentle blue resolves into what it truly is. Particles, countless tiny grains all around you, each one a fleck of glass, a bead of molten silicate, glowing dull and hot, suspended and streaming past you at a speed that makes the air itself a weapon. You're inside the cloud now. You're inside the rain, and the rain is not falling. It is flying, horizontal, a wall of glass moving past you at 7 times the speed of sound, an endless sideways blizzard of mineral that would, if you were anything other than a ghost, sand you out of existence in less time than it takes to form the thought. There is a phrase that one writer used for this, and it has stayed with me because it is so exactly right. death by 1,000 cuts, except that each cut is molten glass moving faster than a rifle bullet. That is the texture of this place at the level where the glass flies. Not a single dramatic blow, but an unrelenting storm of microscopic impacts, each one searing, each one moving at impossible speed, blowing always in the same direction, never slackening, never reversing, never pausing to let anything settle. On Earth, even the worst storm eventually exhausts itself. The front passes, the sky clears, the terrible thing ends, and afterward there is the strange quiet of survival, the dripping eaves, the first bird. Here there is no afterward. The storm is not an event. The storm is the world. It was screaming before the first human being drew breath, and it will be screaming long after the last one is gone, and in all of that time it will not have stopped. Not for an instant, not anywhere. And the heat. As you sink lower, the heat rises around you, climbing past the temperature of a kitchen oven, past the temperature of a blast furnace, past the point where rock softens and the metal glows and runs. The deeper you go, the worse it becomes, the air thickening into something more like a hot, dense liquid than a gas, the pressure mounting, the light from the distant star long since lost above you, until there is only the dull red glow of the planet's own heat and the endless rushing dark. There is no floor to find. You would sink forever into greater heat and greater pressure, into a crushing inner dark from which nothing returns. There is no bottom to stand on, a ground to reach no end to the falling, only deeper and hotter, and the wind always the wind. I want you to come back up now, out of the deep, back to the high blue where the glass flies, and then back out into space, into the cool and the quiet and the dark where the planet is once again only a beautiful blue point glowing against the night. Because here is the thing I most want you to carry out of this descent. From far enough away, none of that horror is visible. From a distance, the planet is serene. It is a jewel. It is one of the loveliest objects in the catalogue of worlds. All of the violence, all of the heat and the screaming wind and the flying glass and the bottomless crushing dark, all of it is folded up inside that calm blue glow, invisible, silent, waiting. You would never know. You could look at that point of light for 1,000 years and never guess what it hides. And there is something in that, something about how appearances and reality drift so far apart out there in the cosmos, that I think is worth carrying with you towards sleep. The most peaceful-looking things are not always peaceful. The most beautiful light can be the signature of the most terrible storm. Stay with me. We are not done. The planet has more to tell us, and the next chapter is about how, exactly, we took its temperature. Part 9. The Map of Fire and Shadow. Years before anyone measured the planet's blue colour or clocked its impossible wind, astronomers built something else first, something that was itself a milestone. The very first map of the temperature across the face of a world beyond our solar system. The year was 2007. The instrument was NASA's Spitzer Space Telescope, an observatory that looked not in visible light but in infrared, the light of heat itself, the glow that warm things give off even in total darkness. And what Spitzer did in the hands of an astronomer named Heather Knutson and her colleagues was watch HD 189733b through an entire orbit and chart how its heat shifted as it turned. Think again about the tidal lock, the eternal day side and the eternal night side. As the planet circles its star, it shows us different portions of those two faces. Sometimes we are looking mostly at the blazing day side, glowing fiercely in the infrared. Sometimes we are looking mostly at the shadowed night side, dimmer and cooler. By measuring how the planet's heat glow rose and fell across a full orbit, the astronomers could reconstruct, like building an image out of a slowly turning silhouette, how the temperature was distributed around the globe. Where was it hottest? Where was it coolest? And, crucially, where exactly on the planet did the hottest point sit? That last question turned out to be the revealing one. You might assume naively that the hottest spot on a tidally locked planet would be the exact centre of the day side, the point that stares straight up at the star, the place receiving the most direct fire. That is where the most energy lands. That should be the hottest. But that is not what Spitzer found. The hottest point was shifted. It was offset, pushed to the side downwind, away from the point directly beneath the star. And that small offset, that displacement of the hotspot, was a clue, one of the very first hard pieces of evidence for the monstrous wind we now know so well. because the only thing that could carry the heat away from where it lands and pile it up somewhere downwind is exactly that wind. A powerful current of air sweeping the heat off the day side and dragging it around the planet before it has time to radiate away. The displaced hotspot was the wind's fingerprint, written in heat years before anyone measured the wind directly. The map also revealed the brutal arithmetic of the two faces. The day side and the night side differ in temperature, but not by as much as you might expect for a world with eternal noon on one half and eternal midnight on the other. The difference between them is real, hundreds of degrees, but the night side is still searingly hot, still glowing, still far beyond anything survivable. And the reason the night side is not frozen solid, the reason it remains an inferno despite never seeing the star, is once again the wind. The wind carries the heat. The wind takes the fire of the day side and hauls it around to the dark side, evening things out, keeping the whole planet roasting. Without that circulation, the night side would be a frozen waste and the day side a concentrated hell. The wind blends them into a single planet-wide furnace, hottest on the day, merely terrible on the night, with no true cold anywhere. And then there is the line between them, the Terminator. On Earth we have a Terminator 2, the moving line of sunrise and sunset that sweeps around the planet as it turns, the soft band of dawn and dusk that you have stood in countless times without thinking of it as a line on a map. But our Terminator moves. It is always travelling, always handing the land from night into day and back again, so that no place lives forever in twilight. On HD 189733b, the Terminator does not move. It is fixed. There is one single ring around the planet, one permanent band, where it is forever neither fully day nor fully night, where the blazing light of the eternal day side meets the shadow of the eternal night side, and they hold, frozen in place for all time, a ring of permanent dusk, a circle of endless twilight wrapped around a world. And it is precisely along that band, where the hot day air rushes toward the cooler night, that the winds reach their most violent and the glass is driven hardest. The most beautiful idea on the whole planet, a ring of eternal twilight, is also the place where the storm is worst. So that was the early gift of Spitzer and the infrared, the heat map, the offset hotspot, the first hard proof that something was moving the air around that world with enormous force. Each new instrument added a layer. Spitzer gave the heat. Hubble gave the colour and the chemistry. The ground telescopes gave the wind. Piece by piece, a planet no one can see was assembled in our understanding, more thoroughly than almost any other world beyond our own, until HD 189733b became something rare, a distant point of light that we genuinely, deeply know. Stay with me, because the next thing we learned about it is perhaps the most haunting of all. This planet is dying. It is being slowly torn apart and blown away into space, and we have watched it happen. Part 10. The world that is bleeding into the dark. For all its violence, you might imagine that a planet the size of Jupiter, a giant ball of gas, would at least be permanent, indestructible on any timescale that matters, sitting out there blue and burning forever. But HD 189733b is not permanent. It is losing itself. Slowly, steadily, the planet is leaking its atmosphere into space, bleeding gas off the top of its air and into the dark, and astronomers have not only deduced this, they have watched it, caught the planet in the act, measured the rate at which it is coming undone. The discovery came in 2010 from a team led by an astronomer named Alain Le Cavalier des Étangs, working with the Hubble Space Telescope. They used a particular trick, looking at the planet in a specific colour of ultraviolet light that hydrogen gas absorbs strongly, a wavelength called Lyman alpha. Hydrogen is the lightest and most abundant gas in the universe, and it is the easiest thing for a planet to lose, the first to be stripped away when a world is under assault. By watching how the planet's transit looked in that hydrogen-sensitive light, the team could see whether there was hydrogen gas spreading out around the planet, escaping beyond the bulk of its atmosphere into a great tinous halo. And there was. They detected an extended cloud of hydrogen around the planet, gas that had climbed up out of the atmosphere and was streaming away, escaping the planet's grip and trailing off into space. HD 189733b became only the second planet beyond our solar system ever caught evaporating, the second world we had ever watched lose itself to the void. Why is it happening? The cause goes back to the star, that restless orange dwarf we met early on, and to the merciless closeness of the planet's orbit. The star pours out extreme ultraviolet light and X-rays, a flood of high-energy radiation, and the planet sits right in the path of that flood, soaking it up. That radiation heats the very top of the planet's atmosphere, energizing the gas there, giving the lightest atoms enough speed to climb away from the planet entirely and escape into space. It is a slow boiling off, an evaporation driven not by the planet's own heat but by the radiation of its star, the star quite literally eroding the planet from the outside in, stripping its outer layers atom by atom and casting them away. The planet is being weathered by its sun the way a coastline is weathered by the sea, except that what is being worn away is the planet's own air, and what is doing the wearing is invisible radiation, and the result is a slow vanishing into the dark. Now, I do not want to alarm you, lying there in the quiet, into thinking this planet is about to disappear. It is not. The amount of gas it is losing, while staggering in human terms, is only a tiny fraction of the planet's enormous total mass. A world the size of Jupiter holds a colossal reservoir of gas, and even bleeding steadily, it is in no danger of evaporating away any time in the foreseeable future. The astronomers were careful to say so. This is not a planet on the verge of vanishing. It is a planet slowly being trimmed at its edges, a giant losing the thinnest outer skin of its atmosphere over enormous spans of time. But the fact remains, and it is a strange and sobering one, that this world is not static. It is not a finished permanent thing. It is in a process. It is changing. It is, in the largest sense, mortal, subject to forces that are slowly and patiently taking it apart, and we happened to look up at exactly the right moment in cosmic history to catch it in the act. There is something almost tender in that idea, and I want you to hold it gently as you drift. Out there, 63 light years away, a planet is quietly coming undone, shedding pieces of itself into the dark, and no one out there knows or mourns or marks the loss. There is no one to see it. The gas simply lifts away, atom by atom, into the great silence, and the planet continues blue and burning, a little lighter for it, indifferent. And on a small blue world 63 light years off, a handful of people pointed a telescope at exactly the right patch of sky and saw it and understood it and wrote it down, so that now you lying in your bed tonight know a true thing about the slow unmaking of a world you will never see. Stay with me. Because the most dramatic moment in this planet's recent history is not the slow steady leak. It is what happened when the star erupted and we were watching and the planet's atmosphere answered. Part 11. The night the star struck back. In 2010, when the astronomers first looked for the planet's evaporating atmosphere in that hydrogen-sensitive ultraviolet light, they saw something almost disappointing. They saw very little. The planet seemed quiet. There was no obvious billowing cloud of escaping gas, no dramatic plume, nothing to suggest the world was bleeding heavily. It looked that year like a planet holding onto its air, and so the team did what good scientists do. They came back, they observed it again, a second time, in late 2011, to check to be sure, to see whether the planet had anything more to say, and this time the planet had everything to say. When they observed 8D189733b in 2011, the picture had transformed completely. Now there was an enormous signature of escaping gas. The planet's upper atmosphere was streaming away, hydrogen pouring off into space at a tremendous rate, the world visibly hemorrhaging its air where a year earlier it had seemed calm. Something had changed dramatically in the time between the two observations. Something had happened to this planet out there in the dark between one look and the next, and the astronomers set out to discover what. The answer came from combining the Hubble observations with data from another spacecraft, a satellite called SWIFT, which is built to watch for sudden, violent bursts of high-energy light across the sky. And SWIFT had caught something. Just before that 2011 observation, the host star had erupted. It had unleashed a powerful flare, a sudden brilliant explosion of radiation, the stellar equivalent of the solar flares our own sun produces, but landing on a planet sitting far, far closer to the fire than any world in our system. The timing told the story. The star flared, blasting the planet with an intense surge of X-rays and ultraviolet radiation, and in the aftermath the planet's atmosphere responded by streaming away far more violently than before. The astronomers had caught, for the first time ever, an alien planet reacting in real time to the violence of its own star. They had watched space weather happen on a world beyond our solar system. The numbers attached to this event are difficult to hold in the mind, and I want to give them to you slowly. After the flare, the planet was estimated to be losing gas at a rate of at least around 1,000 tons every single second. Not every day, not every hour, every second. Stop and let that settle. 1,000 tons of atmosphere, the weight of a small ship lifting off the planet and streaming away into the dark second after second after second in the wake of the star's eruption. And the radiation that drove it was, as we touched on earlier, almost beyond comparison. Accounting for the planet's size and its closeness, the astronomers calculated that during that flare, HD 1-89733b was struck by something on the order of 3 million times the X-ray energy that the Earth would receive from one of our Sun's strongest flares. 3 million times. Whatever idea you have of a bad day, of being battered by forces beyond your control, scale it up 3 million times, and you begin to approach what this planet endured, and endures, every time its restless star decides to erupt. What this revealed, beyond the spectacle of it, was something profound about how planets and stars are bound together. We sometimes imagine a planet as a thing apart from its star, orbiting at a polite distance, lit by it but otherwise independent, going about its own business. The flare on HD 1-89733b shattered that picture. Here was a star reaching out and touching its planet directly, violently, stripping its atmosphere, changing it, eroding it in a single eruption by an amount we could actually measure from 63 light-years away. The planet and the star are not separate. They are locked in a relationship, and it is not an equal one. The star is enormous and powerful and indifferent, and the planet is held close and made to suffer the star's every mood, every flare, every surge, every eruption, with no shelter and no escape and no distance to soften the blow. I find myself thinking when I sit with this about how lucky we are. Not in any grand cosmic sense, just in the plain mechanical fact of our distance. Our sun flares too. It erupts. It throws out storms of radiation and clouds of charged particles, and when the largest of these reach the Earth, they can knock out power grids and disrupt our machines and paint the sky with auroras. But they reach us softened, spread thin across 93 million miles, their fury dispersed by the sheer distance they have to cross. We feel a whisper of what HD 1-89733b feels as a scream. The same kind of force, the same kind of stellar violence, but for us a manageable hazard and for that planet a slow execution. The difference between a habitable world and a dying one, it turns out, can come down to nothing more dramatic than how far you happen to sit from the fire. Stay with me. Because the most recent chapter in this planet's story is also the strangest, and it begins with a smell. Part 12. The World That Smells of Rotten Eggs. In 2024, a new instrument turned its gaze toward HD 1-89733b, the most powerful space telescope ever built, the James Webb Space Telescope. Webb sees in the infrared with a sensitivity and a precision that dwarfs everything that came before it. And when astronomers pointed it at this much-studied planet, they were able to read its atmosphere in finer chemical detail than ever. They were hunting for the specific molecules in that alien air, the fingerprints of particular gases written in the starlight that grazed the planet's edge. And among the things they found was a molecule that, if you could somehow breathe that atmosphere and live, would announce itself instantly to your nose. Hydrogen sulfide, the smell of rotten eggs. There is something almost absurd about it, and I think that absurdity is worth pausing on, because it makes the planet feel suddenly strangely vivid. We have spent all this time describing a place of cosmic horror, a world of impossible heat and screaming wind and flying glass, a blue jewel hiding an inferno, and now we learn that on top of everything else, it stinks. It smells of sulfur, of rotten eggs, the same unpleasant odour you might catch from a struck match or a hot spring or a spoiled meal. Of all the things to discover about a planet 63 light-years away. The astronomers discovered its smell, a small and homely and faintly ridiculous detail, sitting incongruously atop all that grandeur and terror. The most hostile world we know, and it would make you wrinkle your nose. But the discovery was not really about the smell, charming as that detail is. Hydrogen sulfide matters to scientists for a deeper reason. It contains sulfur, and sulfur is an element that astronomers had rarely been able to detect in the atmosphere of a planet beyond our solar system. Finding it here, measuring how much of it there was, told them something about how the planet formed and what it is made of at a fundamental level, about the raw ingredients that came together long ago to build this world. Each element they can identify is another clue to the planet's history, Another line in a story that reaches back billions of years to the disk of gas and dust where the planet was born. The rotten egg molecule was not a curiosity. It was a piece of the planet's biography written in sulfur. The same Webb observations did something else too, something that quietly overturned a long-held assumption. For years, scientists had wondered whether this planet's atmosphere held large amounts of methane, the simple molecule that is so common across the cosmos and that plays such a role in the chemistry of many worlds. There had been hints, suspicions, models that suggested methane should be there, but when Webb looked with all its power and precision, the methane was not there, or rather, it was there in far smaller amounts than anyone had expected. Ruled out at the high concentrations that had been proposed, the planet was simply too hot, its chemistry too driven by extreme temperature, for methane to survive in abundance. One of the lead researchers on the study, an astronomer named Guanghui Fu, summed it up plainly. They had suspected the planet was too hot for much methane, and now they knew it did not have it. This is how science actually moves, and I think there is something quietly beautiful in it that is worth holding as you drift. Not in great leaps, but in patient corrections. A guess made, a hint followed, an assumption built up over years, and then a better instrument arrives and looks more closely, and the assumption falls away, replaced by something truer. The methane that was supposed to be there was not there. The sulfur that was hard to find was found. With each new telescope, each new pair of eyes, the portrait of this planet sharpens, an old guess erased and a new fact penciled in, the blurry sketch resolving slowly into something more and more like the real and particular world that hangs out there in the dark. We will never visit it. We will never stand in its twilight ring or watch its glass fly. But we are coming to know it, truly know it, with a depth that would have seemed impossible to the people who first noticed that orange star flicker in 2005. So now you can assemble the full strange creature in your mind, all of it at once as you lie there in the quiet. A fallen giant the size of Jupiter, 63 light-years away, locked face to face with a restless orange star. One side in an eternal blazing day, one side in eternal burning night, a ring of permanent twilight wrapped around the middle, where the storm is fiercest. An atmosphere of over 1,000 degrees, glowing cobalt blue from a high haze of molten glass, winds of 5,000 miles an hour and more, 7 times the speed of sound, racing forever from the day side to the night side and carrying the glass sideways through the sky. A world slowly bleeding its air into space, struck and stripped by the flares of its star, losing 1,000 tons a second when the fire erupts. And underneath everything, faintly, the smell of sulfur, of rotten eggs, the homely strange final note in a symphony of the impossible. That is HD 189733b. That is the blue planet. Stay with me. Because it is also something more than the sum of its horrors, and the something more is the reason it matters so much to us. Part 13. The most studied stranger in the sky. Among the thousands upon thousands of planets we have now found orbiting other stars, the great and growing catalogue of alien worlds, HD 189733b, occupies a special place. It is one of the most thoroughly studied of them all, a planet returned to again and again across 2 decades by nearly every major instrument we have, a kind of testing ground, a touchstone, the world astronomers go back to when they want to try something new. And the reason for this comes down to a few lucky accidents of geometry and chemistry that made it the perfect subject, the right planet in the right place at the right brightness, almost as if the universe had set it out for us to practice on. It is close, for one thing, just 63 light-years away, which in the vastness of the galaxy counts as practically next door. Its star is bright, easy to find and easy to study, bright enough to gather plenty of light from. The planet is large, a full giant, so it blocks a generous slice of its star's light when it transits, that deep 3% dip that makes its atmosphere easier to probe than a smaller world's would be. And it transits at all, which is itself a piece of luck, because only a small fraction of planets happen to be oriented so that they pass directly between us and their star from our particular point of view. All of these things together made HD 189733 be a gift to astronomy, a planet practically designed for study, and astronomers seized it. And so it became a planet of firsts, a roll call of milestones that reads like a history of how we learned to study alien worlds at all. It was the first planet beyond our solar system to have a map of its temperature drawn across its face, that infrared portrait from Spitzer in 2007. It was among the first to have the carbon dioxide in its atmosphere detected. It was the first whose true overall colour we measured, that famous deep blue from Hubble in 2013. It was one of the first caught evaporating, one of the first watched reacting to a flare from its star, the subject of the first weather map ever made for an alien world. Again and again, when astronomers wanted to attempt some new and difficult feat of measurement, some technique never tried before on a distant planet, they reached for this one, because it was bright and close and generous, and again it gave up its secrets and let us test our tools. Whole careers were built studying this single point of light. Whole new methods were invented and proven on it. Why does this matter beyond the planet itself? It matters because HD 189733b taught us how to read the atmospheres of worlds we cannot see, and that skill, that hard-won ability to take starlight that has passed through an alien sky and decode the chemistry written in it, is the skill on which one of the greatest searches in human history now rests, the search for life, the search for another world like ours. Because the same techniques we sharpened on this blue inferno, the transmission spectroscopy, the careful subtraction of starlight, the reading of fingerprints in the spectrum, are exactly the techniques we will use, are already beginning to use, to examine smaller, cooler, gentler worlds, the rocky planets at the right distance from their stars where liquid water might pool and life might just possibly take hold. To find the signatures of an atmosphere like ours, the oxygen, the water, the faint chemical whisper that might mean something is alive out there, we first had to learn to read atmospheres at all. And we learned to read atmospheres on planets like this one. The blue planet where it rains glass sideways, this most hostile of worlds, is one of the teachers that is helping us learn how to find a world that is kind. There is a strange kind of grace in that, and I want to leave it with you as the chapter closes. The most hostile place becomes the best teacher. The world that could never hold life becomes one of the keys to finding life elsewhere. The Inferno helps us search for the garden. We did not choose HD 189733b because it was beautiful, though it is, or because it was terrible, though it is that too. We chose it because it was reachable, in the limited way that anything 63 light-years off is reachable by the patient instruments of a curious species. And in studying it, in spending 2 decades learning every secret of a planet none of us will ever touch, we taught ourselves how to look outward, how to read the light, how to ask the universe what its other worlds are made of. Stay with me. There is not much further to go now, and what remains is the largest question of all, the one that opens out beneath everything we have said tonight, like the sky opening above a traveller at the end of a long road. Part 14. The Family of Fallen Giants. HD 189733b is not alone in its strangeness. It belongs to a whole family of worlds, the hot Jupiters, and the story of how we discovered that this family exists at all is worth telling, because it changed our entire picture of the universe in a single stroke, and it happened more recently than you might think. For all of human history, right up until the final years of the 20th century, we had never confirmed a single planet orbiting another ordinary star. We had our own solar system, our familiar 8 worlds, and we assumed reasonably enough that other stars probably had planets too, arranged in much the same sensible way. Small rocky worlds close in, great gas giants far out. We had a sample size of exactly 1 solar system, and we built our expectations on it. Then, in 1995, 2 astronomers in Switzerland, Michel Mayor and Didier Queloz, found the first confirmed planet orbiting a normal star like our Sun. The star was called 51 Pegasi, and the planet they found there broke every expectation we had. It was a giant, a world about half the mass of Jupiter, and it was not far out in the cold where giants were supposed to live. It was hugging its star, whipping around it in just 4 days, baking at enormous temperatures. It was a hot Jupiter, the first one ever found, and it should not have existed according to everything we thought we knew. That single discovery, which would later earn its finders a Nobel Prize, told us in one blow that the universe was far stranger and more varied than our tidy solar system had led us to believe. Other planetary systems did not have to look like ours. They could look like nothing we had ever imagined. In the years that followed, as our instruments improved and our searches widened, more and more of these hot Jupiters turned up, and we realized they were not freak exceptions, but a genuine and recurring kind of world scattered throughout the galaxy. Giant planets fallen close to their stars, roasting, many of them tidally locked, many of them with their own violent weather and their own strange chemistry. HD 189733b discovered a decade after that first one, is one of the finest and best-studied members of this family. But it has cousins beyond counting out there in the dark, each one a fallen giant pressed against its own fire, each one with its own particular flavour of hell. Some are even hotter, hot enough to glow not blue but a dull angry red, hot enough that on their day sides not just glass but iron itself turns to vapour and rains down on their cooler faces. There are worlds out there where it rains molten iron. There are worlds darker than coal that swallow nearly all the light that touches them. The hot Jupiters are a gallery of nightmares, and HD 189733b, for all its terrors, is in some ways one of the gentler members of its own monstrous family. Here is something that should make you feel, lying there safe and warm, just how unusual our own situation is. Our solar system has no hot Jupiter. We have no fallen giant baking against the sun, no world raining glass or iron, no roasting monster in a 2-day orbit. Our great planet Jupiter sits exactly where a giant is supposed to sit, far out in the cold, taking nearly 12 years to circle the sun, calm and slow and distant. And because of that, because our giants stayed where they belonged and did not come crashing inward through the inner system, the small rocky worlds closer to the sun were left undisturbed, free to form and settle, and, on at least one of them, to grow gardens and oceans, and eventually creatures who could look up and wonder. In many of the systems with hot Jupiters, the migration of that giant inward may have scattered or destroyed whatever smaller worlds lay in its path. Our quiet, orderly, well-behaved solar system, with its giants politely keeping their distance, may be part of the reason you are here at all, to hear these words. So when you picture HD 189733b now, picture it not as a lone freak, but as one bright and well-known member of a vast hidden population, one face among multitudes, a representative of a kind of world that is common across the galaxy, and that we simply could not see until very recently. Every hot Jupiter out there is its own story, its own particular arrangement of heat and wind and chemistry, the overwhelming majority of them unstudied, unnamed beyond a catalogue entry, glowing and storming away in the dark with no one to witness them. HD 189733b is the one we happen to get to know. It is the family member whose secrets we learned. And through it, we glimpse the others, the countless fallen giants raining their glass and iron across a galaxy that turns out to be far stranger, far more violent, and far more wonderful than we ever dared to guess. Stay with me. There is one more truth about this planet I want to give you before we let it go, and it is the simplest and the largest of all. It is the truth of how far away it is. Part 15. 63 Years of Light. I have said it many times tonight, almost casually, the way you might mention any fact. 63 light-years away. The number has probably stopped landing by now, worn smooth by repetition. So let me give it back to you with its full weight, because the distance to this planet is, in its own quiet way, as staggering as the glass and the wind, and it carries a kind of poetry that I think is the right thing to fall asleep on. A light-year is the distance that light travels in 1 year, and light is the fastest thing there is, the absolute speed limit of the universe moving at 186,000 miles in a single second. In 1 second, light could circle the Earth more than 7 times. In 1 second, it crosses the distance from the Earth to the Moon and most of the way back again. There is nothing faster. Nothing in all of existence outruns light. And yet even light, even that impossible speed, takes a full year to cross a single light year, a distance so vast that the miles in it run into the trillions. The planet we have been visiting tonight is 63 of those light years away, 63 trillions upon trillions of miles, a gulf so wide that the fastest thing in the universe needs 63 years to cross it, which means something quietly profound about the blue light from that planet, the cobalt glow we measured, the light that carries its secrets. That light is old. The light from HD 189733b that astronomers gathered to learn its colour did not leave the planet recently. It left 63 years ago. It set out across the dark while the world you live on was a very different place, before many of the things you think of as ordinary even existed, and it has been travelling ever since, crossing the unimaginable emptiness between the stars at the maximum speed the universe allows, and only now, only in our moment, arriving. When astronomers look at that planet, they are not seeing it as it is. They are seeing it as it was 63 years ago, a portrait carried slowly across the void. The planet that sent that light may have changed in all the time since. The light we read tonight is a letter posted long ago, only now sliding under the door. And this is the gentle, final, humbling truth. We will never go there. I want to say it plainly, without drama, because it is simply true and because there is a strange peace in it. With the fastest spacecraft humanity has ever built, the probes we have flung out past the edge of our own solar system, a journey to HD 189733b, would take not years, not centuries, but hundreds of thousands of years. Far longer than our species has existed. Far longer than recorded history many times over. No person now alive, no person who will be born for a very long time, will ever stand anywhere near that blue point of light. It is beyond us, not because we lack the will or the cleverness, but because the universe is simply, profoundly, almost unbearably large. And that planet sits on the far side of a gulf that no human craft can cross in any span of time that means anything to a human life. And yet here is the wonder of it. The thing that should fill you not with sadness, but with something closer to awe as your eyes stay closed and your breathing slows. We will never go there, and we know it anyway. We know its colour and its temperature, its wind and its weather, the chemistry of its air and the smell it would carry, the way it is slowly bleeding into space and the way its star strikes it down. We know all of this about a place we cannot reach and cannot see, a place separated from us by a distance that defeats the imagination. And we learned it without ever leaving home, from a few dips in the brightness of a star and the patient, brilliant, stubborn work of people who refused to accept that distance meant ignorance. The universe placed that planet impossibly far away, and put it behind the glare of its star where no eye could ever see it. And we found it anyway. We read it anyway. We came to know it anyway. The distance won, in the sense that we will never go, and we won too in the sense that it could not keep its secrets from us. Stay with me. There is just a little more, and it is about the people who did this, and about you, lying there, knowing a planet you will never touch. Part 16. The Patient Watchers. I want to take you for a moment away from the planet and back to here, to the small, wet blue world where this whole story was assembled, and to the people who assembled it. Because it is easy, in a tale like this, to make the planet the only character, to let the glass and the wind and the star carry all the weight. But there is another story underneath it, quieter and close to home, and it is the story of how a species of curious animals on a minor planet managed to learn the weather on a world 63 light years away. That story is made of people and patience and a kind of devotion that I find genuinely moving. Think about what it actually took. Someone had to design and build the telescopes, instruments of glass and metal and electronics so precise that they could detect a star dimming by a fraction of a percent, or measure a shift in colour so small it corresponds to the gentle drift of gas across an alien sky. Someone had to launch some of those instruments into orbit on pillars of fire, lifting them above the blur of our own atmosphere so they could see clearly. Someone had to sit with the data night after night, year after year, stacking observations, fighting the noise, checking and rechecking, separating the faint true signal of a distant world from the endless static of the universe. The French team that found the flicker in 2005, Heather Knutson and her colleagues drawing the first heat map in 2007, Frédéric Pont pulling the blue colour out of the dark in 2013, Alain Le Cavalier des Étangs catching the planet bleeding into space, the Warwick team mapping a wind no one could feel. The teams who turned the great new telescope toward it and found the smell of sulphur in its air. Hundreds of people across decades, across countries, each adding a single careful layer to the portrait, most of them never meeting, all of them contributing to a knowledge that belongs now to all of us, including you. None of them will ever go to that planet either. They knew that. They spent their careers, some of them, studying a world they understood from the beginning they could never visit, never touch, never see except as a shadow crossing a star and a whisper in the spectrum of starlight. And they did it anyway, gladly, because the knowing was enough, because there is a particular human hunger, one of the best things about us, that is satisfied simply by understanding, simply by reaching out with the mind towards something the body can never reach. We are the animals who want to know what is out there, even when out there is 63 light years away and made of flying glass and forever beyond our grasp. We point our instruments into the dark and we ask the oldest question, what is that? What is it really? And we do not stop until the universe answers. And it does answer. That is the part that should settle into you most deeply tonight. The universe is not silent. It does not withhold itself from us out of spite. It hides its secrets behind distance and glare and noise, behind gulfs of space and walls of starlight. But it does not lie, and it does not refuse the patient question. Ask it carefully enough, with instruments precise enough and minds persistent enough, and it will tell you the colour of a planet you cannot see, and the speed of a wind you can never feel, and the chemistry of an air you will never breathe. The blue planet kept its secrets for billions of years only because no one had yet asked. The moment we learned how to ask, it began slowly to answer. So here is where you are tonight. You are a person lying in a quiet room on a small blue world, wrapped in warmth and safety, your body slowing towards sleep. And in your mind now, placed there by nothing more than a chain of patient human work stretching back across 2 decades, is a true and detailed picture of a planet 63 trillion miles times better something beyond reckoning away, a planet you will never see, a place of glass and fire and screaming wind that does not know you exist and never will. You are holding a true thing about a corner of the universe you can never visit. That is not a small thing to carry into sleep. It is one of the strangest and most beautiful privileges of being a human being alive in this particular century, when the instruments finally became good enough and the patient watchers finally learned to read the light. Stay with me. There are still a few secrets of this world we have not touched, quieter ones, and I want to give them to you now while your breathing slows, because they make the planet feel even more real, even more particular, even more like an actual place and not just a list of terrors. Part 17, The Second Sun in the Sky. There is a detail about this world I have been seeing because it adds something almost lonely and lovely to the picture. And it is the kind of thing best handed over softly, late, when you are already half adrift. The blue planet does not orbit one star. It orbits in a system with 2. Its blazing orange sun has a companion. When astronomers looked carefully at the neighbourhood of HD 189733, in the years just after the planet was found, they noticed a faint red point of light sitting close by in the sky. And over time, they proved that this faint red star was not merely a chance alignment, not just a more distant star that happened to lie in the same direction. It was bound. It was a true companion. Gravitationally tied to the orange star, the 2 of them drifting through the galaxy together as a pair. The companion is a red dwarf, the smallest and coolest and most common kind of star there is, a dim ember of a thing with perhaps a quarter or a third of the mass of our sun, glowing a deep, dull red, sipping its fuel so slowly that it will outlive nearly every other kind of star in existence. It is called HD 189733b, with a capital letter, to distinguish it from the planet, which carries the same numbers but a small one. So picture the sky over the blue planet now, if you could somehow stand within its storm and look up. Dominating everything, enormous and close and merciless, the orange star filling a huge swath of the sky, pouring down its light and its radiation. And then, far off in another part of that sky, small and faint and red, a second sun, a distant ember, too far away to warm anything, too dim to do more than glow softly against the dark. But there, a companion light, a second star that has accompanied this whole violent story from the beginning. The blue planet rains its glass beneath 2 suns, one a blazing tormentor and one a quiet distant witness, and it has done so for the entire long age of the system. And here is the gift that faint red companion gave to us, the reason astronomers were so glad to find it. A lone star is a difficult thing to put an age on. Stars do not wear their years openly. But a red dwarf changes in certain measurable ways as it ages, and because this companion was born at the same time as the orange star, from the same cloud in the same moment, finding its age told astronomers the age of the whole system, planet included. An astronomer named Edward Ginnern and his colleagues used exactly this trick, reading the age of the system from the faint red companion, and concluded that this world and its stars are well over 600 million years old. Old enough that the violence we have described is not some passing phase of a young and unsettled system, but the long-established condition of an ancient and stable one. The planet has been raining glass for a span of time that dwarfs the entire history of complex life on Earth. The faint red star, the quiet second sun, is the witness that let us measure just how long the storm has been raging. Stay with me. Because that same long age has given the planet time to do something else, something that turns it from a planet into something stranger, almost into a comet. Part 18. The World with a Tail. We talked earlier about how the planet is slowly bleeding its atmosphere into space, stripped away by the radiation of its star, losing gas off the top of its air. I want to return to that now and follow the gas, because where it goes is part of what makes this world so strange. When the lightest atoms climb up out of the atmosphere and escape the planet's grip, they do not simply vanish. They have to go somewhere. And what astronomers increasingly understand about planets like this is that the escaping gas tends to stream away in a particular direction, pushed by the pressure of the starlight and the wind of particles flowing off the star, forming a long, faint trailing cloud behind the planet. A tail. The blue planet, in other words, may trail a vast tenuous streamer of its own escaping atmosphere, swept back like the tail of a comet. Think about what that means for the picture in your mind. A comet, that icy wanderer of our own solar system, grows its glowing tail because the sun's heat boils gas and dust off its small frozen body, and the pressure of sunlight and the solar wind blow that material out into a long shining trail, always pointing away from the sun. HD 189733b is no comet. It is a giant, a world more massive than Jupiter, and yet, in its own way, sitting so close to its fierce star, it does something a comet does. It sheds, it streams, it trails an invisible plume of its own substance out behind it into the dark, a giant planet behaving just a little like the smallest and most fragile of icy travellers. Astronomers have searched for and studied these escaping streams using the fingerprints of hydrogen and of helium, that second lightest of all gases, watching the planet's transit in the special colours those gases absorb, looking for the signature of an atmosphere reaching out beyond the planet and flowing away. And the signatures are there, sometimes stronger, sometimes weaker, hinting at an escape that ebbs and flows with the moods of the star. That word sometimes points to one more strange truth about this world. Its atmosphere is not constant. It changes. NASA, describing this planet, called its atmosphere changeable and exotic, and the phrase is exactly right. The amount of gas escaping shifts over time, surging after the star flares, quieting when the star is calm. The hazes thicken and thin. The planet is not a fixed and finished object that looks the same every time we glance at it. It is alive with change, restless, responsive, a world whose weather and whose very atmosphere shift from one observation to the next, so that astronomers returning to it year after year find a place that is never quite the same as they left it. And it moves. I have saved this number too because it belongs here with the comet and the tail and the sense of furious motion. The blue planet, racing around its star in that tight 2-day orbit, is travelling at roughly 150 kilometres every second. In the old familiar units, that is around 340,000 miles per hour. 340,000. Our own Earth, ambling around the Sun and in its calm, wide, year-long orbit, moves at about 67,000 miles per hour, and that already seems impossibly fast for something we never feel moving at all. The blue planet hurtles around its star more than 5 times faster than that, a giant world flung around its orange sun at a speed that would carry it from the Earth to the Moon in well under an hour, trailing its faint plume of escaping air beneath its distant red second sun, raining glass sideways the whole way around. Stay with me. There is one last thing the planet's air can tell us, and it is the oldest story of all, the story of where this world came from. Part 19, a biography written in molecules. When the great new telescope read the air of HD 189733b in fine detail, it did not only find the rotten egg smell of sulphur, it found a whole small chemistry, a handful of molecules whose presence and proportions tell, to those who know how to read them, the story of the planet's birth. There was water vapour, the same simple molecule that fills our own clouds and oceans, present in that scorching air not as anything liquid, but as a hot gas woven through the atmosphere. There was carbon dioxide, the gas we exhale and that fills so much of the cosmos. There were carbon-bearing gases and the sulphur, and there were the silicates themselves, the very mineral stuff of the glass, detected as molecules floating in the air, the raw material of the rain caught in the act of being vapour before it cools and falls and flies. Each of these is a clue, and together they form something like a biography. Here is the idea, and it is a beautiful one to drift towards sleep on. A planet is built from the leftover material of the disk of gas and dust that surrounds a young star as it forms. Depending on where in that disk a planet is born, near the star or far out in the cold, it gathers a different mixture of ingredients, because different materials freeze and gather at different distances from the warmth. so the precise cocktail of chemicals locked into a planet's atmosphere. The ratio of this element to that one, the amount of heavy material compared to light, is a kind of fingerprint of where and how the planet formed. Read the air carefully enough, and it tells you the planet's origin, the place of its birth, the journey it took to arrive where you find it, and what the air of HD 189733b suggests, when astronomers read it this way, fits the story we told much earlier, the story of the fallen giant. The proportions of heavy elements, the things astronomers loosely call metals, meaning everything weightier than hydrogen and helium, hint at a world that gathered its substance far from where we now find it, out in the colder reaches of its young system, and then migrated inward over long ages to its final scorching orbit. The planet's own atmosphere remembers a birthplace it has long since left behind. The chemistry carries the memory of a cold and distant origin, even as the planet now bakes against its star. It is, in a sense, an immigrant world, born in one place and living out its existence in another, and it wears the evidence of that long journey in the molecules of its air, where our instruments, 63 light-years away, can read it. I find that almost unbearably poignant, and I want to leave it with you as the science draws to a close. This planet, so violent, so seemingly simple in its horror, a ball of heat and wind and flying glass, turns out to have a history. It has an origin and a journey. It was born somewhere, gathered itself from a particular cloud, drifted inward across millions of years to the place where it now suffers, and it carries the chemical memory of all of that, written in water and sulfur and silicate and stone, waiting in its air for someone clever enough and patient enough to read it. We tend to think of distant planets as static facts, points of light that simply are, but every one of them has a story like this, a birth and a wandering and a long becoming, and almost all of those stories will never be read, because there is no one near enough to read them. The blue planet's story we have read, a little of it, the opening pages, the broad shape of its origin caught in the fingerprints of its air. Stay with me just a little longer. Let me take you back out there one final time gently for a last look at the blue planet before we let it go. Part 20. One last look at the blue planet. Come with me out there one final time. Not to descend into it now, not to stand in the storm, just to float at a quiet distance and look, the way you might look at the sea from a cliff top on a calm evening, near enough to feel its presence and far enough to be safe. The orange star burns steady off to the side, its amber light pouring out into the dark. And there, held close against it, is the blue world, glowing softly, turning its eternal day face toward the fire and its eternal night face toward the dark, the way it has for billions of years and will for billions more. From here, in the silence and the cold, it is only beautiful. You cannot hear the wind. There is no air between you and it to carry any sound, and even if there were, no scream could cross that gulf. You cannot feel the heat. You cannot see the glass flying, cannot make out the ring of twilight or the displaced hotspot, or the thin halo of hydrogen lifting slowly off its top and trailing away into the night. All of that is there, all of it true, all of it happening right now in the planet's own present, the storm raging, the glass flying, the star striking it down. But from this distance it is folded away, invisible, hidden inside a calm cobalt glow, and what you see is simply a small blue light, steady and serene, one jewel among the countless lights of the galaxy. And I find that I do not want to leave you with the horror of it after all. The horror is real, and it was worth knowing the heat and the wind and the flying glass and the slow bleeding into the dark. But the longer I sit with this planet, the more the horror